Welcome to the 85th Theoretical-Physics-Colloquium by Professor Brian Metzger from Columbia University. He received his PhD in 2009 from University of California at Berkeley. After that, he had a postdoctoral position at Princeton University. He was there a NASA Einstein Fellow between 2009 and 2012. Then briefly, he was Lyman Spitzer Junior Fellow, and then he became a faculty member in 2013 at Columbia University. He was promoted to a full professor in 2020. Over the years, he received a lot of different awards and honors. I will not be able to list them all. Let me just briefly pick a few. Like in 2009, he got his dissertation prize from American Astronomical Society in High Energy Astrophysics Division. In 2014, he received Alfred Sloan Research Fellowship. He became Scilog Fellow from Research Science Corporation in 2016. Received Bruno Rossi Prize from American Astronomical Society in 2019, and the same year, New Horizons Breakthrough Prize in Physics. In 2020, he became a Blavatnik National Laureate in Natural Sciences and Engineering. He is involved in deeply in professional service, organizing many conferences, working on panels, and many other things. For example, in 2020, he was participating as a program panelist in the decadal survey of astronomy and astrophysics. His research interests are very wide in astrophysics, ranging from kilonovas, supernovae, stellar mergers, physics, multi-messenger astrophysics, accretion disks, fast radio bursts, and many other things. And today he will be speaking about shining new light on the physics of neutron star mergers. And with that, I'll give the microphone to Brian.
Thank you for the introduction. It's a pleasure to be here remotely. So yeah, today I'm going to talk a little bit about my work on the electromagnetic counterparts of neutron star mergers. I'm going to focus on the use of these events as probes of the formation of some of the heaviest elements in the universe and ways they may tell us something about the composition of neutron stars indirectly. And even though we've only seen light from one neutron star merger, as you probably are aware, 4 years ago now, I want to give you my own take on that event and hopefully spell out some of the diversity of electromagnetic emissions we may see from future events that hopefully will be testable in the next few years as LIGO's sensitivity range increases and it's able to see more of these events and really fill out this full picture of these spectacular events. So there's different ways to motivate understanding neutron star mergers. One of them is sort of to think about one of the goals of nuclear astrophysics, which is one topic I'm working in, which is really to identify, when and where in our universe the elements that make up the periodic table were forged. Of course, the lightest elements like hydrogen and helium were primarily created in the Big Bang. When you talk about the sort of intermediate mass elements, like the elements of life, most of them were formed in massive stars and expelled into space when those stars explode as supernova. So this is showing you the Cassiopeia A supernova remnant, which exploded about 350 years ago, was potentially the last, galactic naked eye supernova. If anyone was looking, we're not sure. The original star was about 17 times the mass of our sun. And what you're seeing here are X-rays that were produced as the ejecta from that explosion ran into the medium surrounding the original star. And different colors here that you're seeing are basically corresponding to the emission from different elements, X-rays, recombination from different elements. And so you can see, the direct signatures of silicon, sulfur, calcium, iron. And so this is sort of the empirical basis for this famous Carl Sagan quote about, the carbon in our apple pies, et cetera, were formed in the interiors of collapsing stars. We are made of star stuff. Well, the sort of proof is directly in front of you. We see these stars that are exploding and polluting the interstellar medium with these elements, which then form the subsequent generation of planets and allow life like us to exist. But when you get to the bottom of the periodic table, the origin of roughly half of the elements heavier than iron, those produced through the so-called rapid neutron capture process, their origin astrophysically is far less certain. Even though for a very long time we thought that they also came from supernova, it's not so clear anymore, as I'll get to. And nevertheless, this includes, many of the precious metals like gold, silver, and platinum, and the transuranic elements. And obviously, our society and culture would would have evolved very differently if these elements existed on Earth in much different abundances than they do. So it behooves us to try to understand where these elements are coming from. And this is actually, forming these elements is a challenge because, you can form elements up to iron inside of stars, but to get to heavier elements, not only are you dealing with the fact that there's less nuclear binding energy released, but also you have this prohibitive Coulomb barrier that you have to overcome in these type of nuclei to form heavier elements through standard thermonuclear fusion. But there is a way to get around this old problem of how you turn iron into gold, and that's that you take an iron nucleus and you bombard it at a very high rate with free neutrons. And neutrons, of course, don't have to overcome the Coulomb barrier. So in this way, you can form a very heavy, admittedly radioactive isotope, which then can decay into an isotope like the gold, stable isotopes of gold on Earth. The challenge then shifts to where in nature do you find such a high abundance of neutrons, such a high density of neutrons that you can bombard an iron nucleus at a very high rate with those neutrons. Because neutrons in vacuum, as we know, are unstable. They decay into protons in about 15 minutes. So we have to find, we know that the R process, the site for creating these heavy elements through rapid neutron capture, we know it must be a rare and in some sense explosive astrophysical event because it has to produce this very high flux of neutrons. And of course, the place you go to find neutrons is a neutron star, where the neutrons are stable because the interior of the star is so dense that they're forbidden from beta decay. We're still trying to understand a lot of the properties of trying to move my so I can see the top of my screen, but we're still trying to understand a lot of the properties of neutron stars, particularly what holds them up against gravity. What is their equation of state? There's a lot of uncertainty as to the constituents inside neutron stars. Is it just neutrons and protons? Are there hyperons? Are there free quarks, etc.? And different equations of state make different predictions for what the radius of neutron stars should be as a function of mass. And we're still kind of debating. There are nice measurements now from NICER and LIGO. I'll get to that, but we're still sort of debating whether the neutron star radius is closer to 10 or 11 kilometers or maybe 13 or 14 kilometers. And then we also, of course, another property of the neutron star equation of state, which will inform what I talk about later, is the maximum stable mass of a neutron star. How massive can a neutron star be before it becomes unstable and collapses into a black hole? And we have constraints on this because we can measure pulsar masses in a number of systems. The current record breaker with a well-constrained mass is around 2 solar masses or a bit higher. So we know that the equation of state must support a non-rotating neutron star up to around 2 solar masses, but beyond that, we don't, really know how much more massive they can get. Of course, different equations of state predict different maximum masses, but this is an uncertainty which enters in what I'll be describing. So, of course, if you get 2 of these neutron stars in a binary system that's sufficiently compact, it will emit a sizable quantity of gravitational waves. And this causes the binary to inspiral with time at an ever accelerating rate. And this gravitational waves that are produced by this inspiral, of course, are increasing in frequency and amplitude as the 2 stars approach each other. I think we're all aware of this, and this produces this chirp-like gravitational wave signal to which LIGO and Virgo detectors are sensitive. And you're probably also aware that in 2017, August 17th, LIGO detected its first neutron star merger. We call it 170817 based on the date of discovery. Although LIGO doesn't particularly measure the individual masses of the neutron star all that well, there's some degeneracy in the individual masses. One thing that's interesting to me is that they do measure the total mass of the binary pretty accurately. So in this particular case, the total mass was about 2.74 times the mass of our sun, which, as I'll come to later, is kind of smack dab in the middle of the population of neutron star binaries in our galaxy. So for all we can tell, this may be a pretty typical kind of neutron star that would exist in our own galaxy that we're aware of that will eventually merge. So the gravitational waves arrived on Earth, and by essentially triangulating their arrival times in the 2 LIGO detectors in North America and then the Virgo detector in Italy, they were able to pinpoint the direction of this merger to the constellation of Hydra. And so I just want to go quickly through what happened following that discovery to highlight some of the way this went down. Essentially, when LIGO discovered the event, this sort of triggered a campaign of electromagnetic follow-up from both ground and space. Essentially, every telescope available was pointed towards that part of the sky where this neutron star merger occurred. So the first thing that happened is within a few seconds of the end of the in-spiral, there was a burst of gamma rays detected by NASA's Fermi satellite. It was also detected by the Integral satellite. And so it was localized to this region of the sky. A few hours later, LIGO released its error regions, and that localized it to this green patches here. And then Virgo also contributed information which further localized it to this 30 square degrees. And then several groups essentially either tiled this whole region or looked at these individual galaxies before identifying the counterpart in this galaxy NGC 4993 at about 40 megaparsecs. And so this was, essentially just right in our backyard. And in fact, now we know that the rates of these events are pretty rare. Getting a neutron star merger this close may be kind of a once in a decade event. So we were very lucky that the first event happened so close to us in a galaxy that already had a name. So what was found was this essentially this fading optical counterpart. So this is the galaxy, and then they noticed there was this bit of light that was very quickly dimming. And we see supernova all the time, but this was quite atypical in its properties. It was fading away very, very rapidly. And so sort of immediately apparent to the various groups that were involved with this discovery that this was unlike anything we'd seen before, and was clearly associated with this gravitational wave event. So for the rest of my talk, I want to kind of go through our understanding how we essentially, had predicted this type of signal, what the physics is that controls this rapidly fading blue and then red emission from this event, and what it's taught us about these events as sources of heavy elements. So to do that, I want to go through some of the different outcomes of a neutron star merger. It turns out that there are actually multiple possible outcomes of neutron stars merging, and I want to go through some of that diversity. And the outcome is most sensitive to 2 properties. One is the total mass of the ingoing binary, which, as I said, is something LIGO measures pretty well. And the other is the maximum mass of a non-rotating neutron star, which I told you earlier is uncertain. We know it's larger than about 2 times the mass of our sun, but the maximum mass is uncertain. So what numerical relativity simulations over the past few decades have shown, of course, the in-spiral itself takes a very long time, but then once the 2 neutron stars merge, the dynamical time at that point is typically milliseconds or less. So what numerical relativity simulations have shown is if the total mass of the binary exceeds about 30 to 60% of the maximum mass of a single non-rotating neutron star, the outcome of the merger is essentially a dynamical collapse of the system to a black hole. So essentially most of the material ends up in the black hole. There's very little material outside. And we'd expect in this case a fairly dim counterpart, because all the counterparts I'll talk about have to do with the fact that matter is remaining outside of the horizon following the event. So these prompt collapse events, which are the most massive binaries, are probably pretty dim electromagnetically. What happens, we think, more frequently is the 2 objects coalesce and they form a differentially rotating hypermassive neutron star. So it's rotating faster on its outer parts than in its core. And as a result of this differential rotation, it's essentially temporarily stabilized against collapse to a black hole. Now, we think that this is not the minimum energy configuration for such a star. It wants to be in solid body rotation. And so there will be some sort of internal viscosity, the origin of which we're still trying to understand, that will bring this differentially rotating remnant into solid body rotation, cause mass to accrete towards the center of it, and will destabilize the object and cause it to collapse into a black hole. Now that, we think the naive twiddly estimates suggest, if this is some kind of magnetic torquing, that this should be quite rapid. Within tens or hundreds of milliseconds after the event, this object will destabilize and form a black hole. But as a result of that transport of angular momentum outwards, the black hole now has a more massive torus of material around it, up to a few tenths of a solar mass in a disk around the black hole. It's even possible, however, for sufficiently low mass binaries that even once this object comes into solid body rotation, it still is stable rotating near breakup as a solid body neutron star. We call this object a supramassive neutron star. And it actually has to lose angular momentum in bulk. It has to spin down in order to collapse to a black hole. And depending on the process causing it to spin down, whether it's magnetic dipole radiation or some kind of secular gravitational wave losses, this could be substantially longer. It could take days or weeks in principle before the black hole is formed. So just by changing the ingoing mass by tens of percent, you may get, in this case, I should also say that this object could release a lot more energy into its environment because you can tap into the rotational energy of this object before it forms a black hole. So just changing by 10% the ingoing mass, you produce qualitatively different outcomes for the counterpart. LIGO is able to measure the in-spiral, but it doesn't have a lot of high frequency sensitivity currently to detect the outcome here. So this is sort of the goal of observations. Electromagnetically, we want to infer what's coming out, and then combining that, we can test this picture, and we can also maybe constrain the equation of state because these different channels depend on the maximum mass and radius of a neutron star. I'm going to argue later, if I have time, that 72817 likely went through this intermediate channel where it didn't immediately collapse to a black hole, but it did fairly quickly after the event. So here I'm showing you a numerical relativity simulation, hydrodynamical simulation in GR of two merging neutron stars. You're just seeing the final few orbits. The two stars will significantly tidally deform each other. You'll get matter ejected out of the outer Lagrange points of the binary near the end. We call this the tidal material. The two stars collide. They produce this hot oscillating remnant, which is also ejecting matter in a more spherical fashion. But there's so much angular momentum that this object has a disk around it, and it's eventually losing enough angular momentum or redistributing it to collapse into a black hole. But there's a fairly massive torus sitting outside of the black hole at the end. What types of electromagnetic counterparts we get from these events are expected to be a sensitive function of our viewing angle with respect to the original binary axis, which defines the angular momentum axis of the accretion disk. For 17817, we know we were observing this event about 20-25 degrees off of the axis from the gravitational waves, and knowing the distance, you can infer the inclination of the binary. The idea has been around a long time that the accretion of this disk, going back to the 80s, that the accretion of this disk onto the black hole could power a relativistic jet, and internal dissipation within that jet of some form, shocks or reconnection, could accelerate gamma rays, accelerate particles which produce relativistic particles which produce gamma ray emission. But the idea was, you to see that gamma ray emission, you had to be within the opening angle of this jet, because the whole flow is moving out relativistically, so it will be relativistically beamed into a fairly narrow opening angle, which from other observations we infer in short gamma ray bursts to be about 1/10 of a radian. But in this event, we were observing at about 4/10 of a radian outside the jet. So it was a bit of a surprise that we saw gamma rays at all from this event, given its inclination. But we did nevertheless see gamma rays that were interestingly delayed by about 2 seconds with respect to the end of the in-spiral. And there are different ideas about what caused this delay in terms of the arrival of the gamma rays. Obviously, it could in principle be some difference between the speed of light and gravitational waves. But in terms of other explanations, one possibility is that it took a period of time for the black hole to actually form, and you may need a black hole to create this relativistic jet. It could also be that the jet was formed immediately, but it has to break out of this cloud of debris that was produced during the merger process, and the cloud of debris is itself moving out at a substantial fraction of the speed of light. So once the jet sort of escapes out of this region, there's sort of a delay until it can reach out to a region of low optical depth and emit its gamma rays. So there's still an open mystery here. There's a lot of interesting work being done on this gamma ray burst, which is not the main focus of my talk. I want to talk about the more isotropic signal that's produced by the radioactive decay of the bulk of the material, not the material expanding close to the speed of light, but the subrelativistic material, which is ejected in a more 4π kind of direction that you could in principle see from these events, even if you were viewing it substantially off of the jet axis. And the main point here is that there's different sources of neutron-rich ejecta during these mergers. Maybe not surprising because it's a neutron star that the material that's ejected is also neutron-rich. It turns out this is not trivial, but so as a function of time after the merger, there are different sources of ejecta people discuss. So there's the dynamical material, which is released, basically what I showed you in the video. That's what's released on the dynamical time. You capture it with one of these numerical relativity simulations. And typically this is amounting to maybe 1,000th of a solar mass, maybe in extreme cases 100th of a solar mass. It comes out very, on the dynamical time, which is milliseconds or less, and it tends to have a fairly high velocity. But then you also have another source of ejecta, which are outflows from the post-merger accretion disk. So disk winds from the same accretion disk, which is feeding the black hole and powering the gamma ray burst jet. And this, as I'll talk about in a second, these outflows tend to be significantly more massive than the dynamical ejecta. And they come out over timescales of seconds, which is essentially the viscous time of this torus to accrete onto the black hole, with lower velocities of about a tenth the speed of light. So I'll argue later that we have pretty good evidence that the disk winds were the dominant source of mass ejection in 170817, which is something I've been arguing for a while. One other thing I want to say, though, is that it will turn out that the composition of these outflows, how neutron-rich they are, will actually affect the signal we see. An important thing I want to emphasize is that the exact composition of these disk winds will probably depend sensitively on how long it takes the neutron star to actually, in the center, to collapse to a black hole. And this is because neutron stars, these neutron star remnants in these objects are formed extremely hot. And so they're a very powerful source of neutrinos. And these electron neutrinos can turn neutrons back into protons through this reaction. And so the longer this remnant survives in the center, the more proton-rich the outflows from the accretion disk will become. And this will play an important story in my talk later. I just wanted to point it out here. So the important point in this context is that black holes in this context are fussy eaters. If you try to feed a black hole at a solar mass per second, not all of that matter actually ends up in the horizon. A significant fraction is ejected and wins. This is showing a 3D GRMHD simulation we did with a former postdoc, now professor at Perimeter Institute, Dan Siegel, where we showed sort of the self-consistent generation of turbulence in the disk through the magnetorotational instability. We showed that these disks, because of the dissipation of the MRI, can become quite hot in the midplane. So hot, in fact, that the disk is able to cool effectively through neutrino emission in the midplane. So the midplane is in some sense radiatively efficient. That matter is able to make it into the black hole by cooling. But the upper regions of the disk where a lot of the turbulent dissipation is taking are not able to cool because they're not hot enough in some sense to cool, because neutrino cooling is a sensitive function of temperature. And so pressure gradients tend to drive these powerful outflows from the coronal regions of these disks. And what we find is that only about about 70% of the initial torus mass makes it into the black hole, and about 30% is ejected in these outflows. And the typical outflow speed is about a tenth the speed of light. So even without invoking any type of ordered magnetic field in the disk, just these kind of thermal driven outflows aided by the energy released by alpha particle formation as well tend to produce outflows with about a tenth the speed of light and about 30% of the torus mass. So as this matter is expanding into space, whether it represents, whether it's coming from the dynamical material, whether it's coming from one of these accretion disk outflows, it's decompressing from enormously high densities and temperatures. And what happens first is that the protons and neutrons, some of the neutrons and all of the protons get together and form these heavy seed nuclei through standard thermonuclear reactions. They're a bit heavier than iron. But then you have so many neutrons left over because your outflows are so neutron rich that these neutrons then are able to bombard these seed nuclei and form these heavy R process elements. And so, and this is the way, within a few seconds of the ejection in these outflows, you can form heavy elements in the material. So here I'm showing you a nuclear reaction network. This is neutron number, this is proton number. We're following a single fluid element as it decompresses from high densities and temperatures. along the top, we're following the instantaneous composition of the material as a function of its atomic number here. And so you're going to see as neutron captures essentially move you to the right in this diagram, beta decays move you up to the left. We start off with this distribution of seed nuclei and essentially a nuclear statistical equilibrium. But then as my fluid element decompresses, I capture neutrons, I beta decay, capture neutrons, beta decay, and I form this whole wide range of different isotopes, which eventually after about a second, you run out of neutrons and then everything slowly decays back to the stable valley of the elements over timescales of seconds, days, weeks, months, etc. And so at the end of the day, if you have enough neutrons in your outflow to actually capture your way up to the heaviest elements, you produce those elements. And so these types of simulations make predictions for the abundance distribution, which you can compare, for instance, to that on the sun or metal poor stars that have been polluted by some of these R process events. And so this is the second R process peak and the third R process peak. Just showing the point is not to reproduce the observations exactly, because there's a lot of uncertainty in the nuclear physics that goes along here, but just to show qualitatively, at least, or semi-quantitatively, that the conditions in these accretion disk outflows are sufficiently neutron-rich to form a wide range of these different isotopes. The important point for the kilonova, however, is that these isotopes you create are not stable; they're radioactive. And as they decay back to stability, that releases heat in the form of beta decays, fissioning, alpha decays. And that heat keeps the ejecta hot. It would otherwise just lose all of its thermal energy attained from the merger due to adiabatic expansion before it's able to radiate because of the high optical depths through this material. But because of this heating, it basically keeps the matter hot and allows it to glow. So this is showing you the radioactive power, specific heating per gram per second as a function of time after the merger. If you had a single isotope like nickel 56, as we have in, say, 1A supernova, you get a constant heating followed by an exponential decay. But here you have hundreds of isotopes. So the ones with short half-lives decay into ones with slightly longer half-lives. And when you add them in aggregate, you get something which is more like a power law in terms of the heating rate. And this was, essentially in 2010, we were the first to calculate this. And the important thing is actually what the heating is doing on timescales of hours or days or weeks after the event, because prior to this point, there could be a lot of heat released, but the ejecta is still opaque, so none of that energy gets out as light. But starting a few hours to days to weeks, that energy can start to escape. And so how much energy you deposit in the ejecta on this timescale determines how bright the corresponding emission is. And so we're able to make actual calculations for what the light curves of these events would look like. So this is showing you the bolometric luminosity as a function of time for one of these first models we ran. As I mentioned, so this was for a model with 1/100th of a solar mass expanding at 1/10 the speed of light with this heating rate. So prior to about a day or a few hours, the ejecta is opaque. So not much light is getting out, but then about a day after it peaks, a little less, and then it decays kind of following the input from radioactive heating. When we did these calculations, we found that the events we predicted were about 1,000 times brighter than a nova, which is a galactic event, which is much more common. So we call these events kilonova, and the name has effectively stuck since then. So following 170817, I was hearing as the data come in, and I basically just overplotted these first models we ran with the observed light curve of this event. And I'm not claiming this is a detailed fit, but it was very striking to me that our very first models explain this decay. And so I was, it was quite clear to me that what we were seeing was an R process powered event from 170817. Okay, so this was the first time we had directly observed the production of these heavy elements in nature. And so you can ask, are neutron star mergers, are they enough to produce the gold on Earth? This is a question going back to famous works by Burbage, Hoyle, and Fowler and Al Cameron in the 50s, where they first identified the R process as a nuclear physics phenomena, and then but hadn't yet identified. We've been the last 70 years have been trying to figure out where it occurs in nature. So the production rate of these elements, our process elements you need to produce in our galaxy prior to the formation of the sun to explain their abundances on Earth is about 10 to the minus 6 of these per solar masses per year. And now, thanks to LIGO, we have a measured neutron star merger rate, although it's still enormously uncertain. But you can then ask, what is the rate of neutron star mergers in the Milky Way? And therefore, what would be the required R process yield per merger if I wanted to explain their abundances on the Earth? And that number is uncertain by 2 orders of magnitude, but it's within between a few thousandths of a solar mass and a few hundredths of a few tenths of a solar mass. And this single event, as I'll come to in a second, produced a few hundredths of a solar mass of the R process. So we can't yet say this is the dominant site, but we could say it's probably at least 10%, and it could be 99% of the R process are coming from these mergers. I did not yet talk about the actual color evolution of this event. So it started off extremely blue during the first days with a peak in the ultraviolet, and then over the course of a week, it became extremely red. And this behavior was also predicted by work from Dan Kaysen. The fact that you could get this very red emission from these events. So to understand, basically, the colors of the kilonova are telling you something about precisely which R process elements were created in the event. Because the opacity source in the ejecta are basically a forest of atomic absorption lines. And the higher the density of atomic lines per wavelength affects how well the ejecta is at blocking UV or optical light. If you have just the lighter R process elements, they have a fairly simple atomic structure. Their electrons are in a D shell valence structure, and they have relatively few atomic transitions per unit wavelength, speaking very colloquially. And so they have a fairly low optical UV opacity. So if you have just the light R process elements, you predict a fairly blue event that peaks quite early because of the lower opacity. On the other hand, if you have just a small quantity of the heaviest elements, the lanthanides and actinides at the bottom of the periodic table, they have F shell valence electrons in a combinatorial sort of way. There are many more ways to shuffle the electrons around in the atom, and many more atomic transitions. And so this produces a forest of UV optical lines, which basically block out the light. So if you have these heavy R process elements, you predict something that is peaking in the infrared relatively late in time, relatively cool colors, versus if you just have the light ones, you predict something that's blue and evolving faster. And whether you get light or heavy R process elements depends on how neutron-rich your material is. If you have enough neutrons, you can capture your way all the way up to these heavy elements. If you have fewer neutrons, you can only form these lighter R process elements. So the colors of this event are telling us something about basically the stratification in the ejecta of the heavy elements. And this was also kind of anticipated because we expect that most of the matter that's ejected in the polar regions, it's more irradiated by neutrinos, which, as I mentioned earlier, can tend to turn neutrons back into protons. So we kind of theoretically anticipated that the different sources of ejecta that may be coming sort of fastest out and directly at the observer initially may be primarily these lighter R process elements, whereas matter that comes out in the tidal tails or from the accretion disk outflows once a black hole is formed, we expect that these may be more neutron rich and produce this redder emission. And so, as I said, even several years before this event, it was kind of expected we might see something blue followed by something red. And that's kind of what we saw with this event. So people have done some extensive modeling of the event to actually determine how much mass and velocity are in these sort of two components. There's more sophisticated models of this going on now, but basically we have a fast blue component, which is the lighter R process elements, and a slower, possibly equatorially concentrated red component. The blue component contains about 1/100th of a solar mass expanding around 0.3 C, and the red component, meaning the component also having these heavier elements in it, is maybe about 4 times that or a bit more, expanding around a 1/10 the speed of light. So what I mentioned earlier, there are all these different sources of ejecta from the mergers: dynamical material, accretion disk outflows. what dominated in 1708-17? Well, here I'm just showing the ejecta velocity as a function of the ejecta mass. And this is what we inferred from the kilonova for the blue and red component. Basically, the blue one is here, high velocity, low mass, and the red one is over here, high mass, low velocity. And the points here are all showing you the dynamical ejecta predictions from a suite of numerical relativity merger simulations. And what you see is that some of them kind of overlap the blue kilonova, so it's possible, although I think there are problems with this, that the blue kilonova could be at least partially a dynamical ejecta component, but none of them get anywhere near the bulk of the ejecta from this event that has a lot of mass and a low velocity. And as I mentioned earlier, this is consistent with what we expect from the accretion disk outflows from our numerical simulations of this. So my view is which were also predicted before 1708-17. So my view is that most of the ejecta from this event did not come from what you see when you see a pretty simulation of the merger. It actually came following the merger from the accretion disk outflows. Another thing I want to say is that we can learn something from the kilonova colors so under the assumption that the disk outflows are the dominant source of mass ejection. We can actually learn something about the time scale it took a black hole to form based on those colors. And the idea is something I mentioned earlier, that basically in the center, before a black hole forms, in the center of this remnant, you have a neutron star, which is an extremely strong source of neutrinos. And neutrinos, as I mentioned, in this context, tend to turn what is a neutron-rich disk material and make it more proton-rich. And the longer the object survives, the more it will irradiate this disk, and the more less neutron-rich the disk will get, and as a result, it will produce more blue emission and less red emission, following what I said here. So we did a series of simulations in 2014 with Rodrigo Fernandez, where we basically put a neutrino light bulb in the center of an accretion disk, and we calculated the ejecta composition, whether it would produce the red or the blue kilonova, as a function of the lifetime of the neutron star. So we artificially collapsed it to a black hole, 10 milliseconds, 30 milliseconds, 100 milliseconds, 300 milliseconds, or infinity after the merger. And what we found was exactly this effect, that if the black hole forms promptly, most of the disk outflows are quite neutron rich, and they would form the red emission consistent with what we saw from 1708-17. But if the remnant had survived for seconds before forming a black hole, or several hundreds of milliseconds, we would have expected it basically to turn the entire kilonova blue. And so this is just showing this schematically in terms of the light curves for a prompt collapse case versus a long-lived, meaning 100 milliseconds in this case, neutron star. This is work in collaboration with Dan Kaysen, showing the sort of blue component becoming dominant over the red one. And we basically saw something, kind of like this intermediate case. And so I would argue that, at least qualitatively, the fact that we saw a large quantity of this red kilonova from 1708-17 disfavors a very long-lived neutron star remnant. So implicitly favors that a black hole did form from this event. So going back to my merger pathways scenario, so LIGO was able to measure the ingoing binary mass for this event quite well. We can basically rule out a prompt collapse because there's just way too much ejecta inferred from the kilonova. The prompt collapse, is not going to produce as much as we saw from this event, most likely. We can also rule out, most likely, that this object formed a very long-lived neutron star, both based on the colors of the kilonova and also the fact that the supermassive neutron star has to emit quite a bit of rotational energy to form a black hole. And there's really not that much kinetic. If you add together the energy in the gamma ray burst jet and the kilonova, it's not that much energy, which sort of disfavors that there was a lot of rotational energy injected into the environment by the remnant neutron star. So I think this is a little bit less solid, but you can basically, I think, also argue against a very long-lived remnant. So almost by default, we kind of inferred that 1708-17 likely did form a black hole, given the colors of the kilonova, given everything together. And this, again, was kind of the anticipated vanilla scenario prior to this event. So there was some prior that this is what we would most likely see. And as far as I can tell, it's consistent with that. So interestingly, you can go back to this equation of state diagram that I showed you earlier, where I said we don't know what the neutron star equation of state is. But a given equation of state predicts, the radius of a neutron star and the maximum mass that it can achieve. And you can ask, what do these different constraints that we're inferring, the fact that it didn't undergo a prompt collapse and it didn't form a very long-lived neutron star, how does that factor in on this diagram? And it factors in something like this. So basically, based on the fact that I didn't say this, but the prompt collapse threshold, whether this is 30 or 60% above a maximum mass, depends on the compactness of the neutron star. So using the observed binary mass and the fact that it didn't prompt collapse, there have been various groups who have used this in essence to put a lower limit on the radius of the neutron star with slightly different results between the groups. Probably the more robust one is the Bauswein one here. He has some more recent work on this, but basically you have a lower limit of around 10 point something coming from that. You also have an upper limit on the maximum mass of a neutron star based on the fact that we didn't form a very long-lived stable object. And this is also a little fuzzy for reasons I could talk about, but we don't think the maximum mass neutron star can be, above 2.5 or something. Probably our limit is around 2.2. And interestingly, LIGO, based on the gravitational waves alone and the fact that they didn't detect the tidal deformability, they're able to put like an upper limit on the radius. And then now with NICER, we're getting additional constraints. So it's quite interesting though. This single event was really starting to constrain the equation of state from different directions. And this is a truly multi-messenger constraint because all the red, the blue is coming from gravitational waves alone, but the red are coming from inferences we inferred electromagnetically, coupled with information from the gravitational waves on the binary mass. So this field, is bright. We expect to detect more of these mergers now with LIGO's 04 run, which is in about a year or so. They're upgrading to A+. There'll be third generation detectors, hopefully following that. So we're going to see more events like 170817, maybe observed from different angles. So we'll be able to explore the angular structure of our signal. We hope to see different ingoing properties of the neutron stars, more massive ones, less massive ones. I didn't talk about it, but black hole neutron stars, they've actually seen a few of those now in 03 with no observable counterparts as far as we can tell. And that's probably because the neutron star was swallowed whole by the black hole. For a more rapidly spinning black hole or a lower mass black hole, we may be able to get a counterpart from those, which are qualitatively similar to those I talked about from neutron star mergers. So let me just go through what are the predictions of this scenario. I argued that 1717 was kind of the vanilla outcome. If we do get a prompt collapse, there is less mass ejection, less neutrinos around to turn neutrons into protons. So overall, I don't want to get into specific predictions, but I will say I expect that the event will be dimmer than this event and probably redder because the tidal ejecta is more important in this case, and that's very neutron rich. So we had a chance to test this in principle. LIGO detected a second neutron star merger, 190425, which was substantially more massive than 170817, which, as I mentioned earlier, was consistent with the galactic double neutron stars. So this was the mass posteriors for 190425. And so we would have expected this event, given what we know about the equation of state, we would have expected this event to be a prompt collapse event. Unfortunately, the error region on the sky, I think only one of the LIGO detectors was operational or getting good data or something. And so the error region on the sky was enormous. And although there were many efforts to try to find a counterpart, none was discovered. But I don't think we can really rule out that we covered the full parameter space down to the depth to detect this. So if we get another event where we have a better sky error region like this one, it will be a good case to look for a dimmer red or kilonova. What about the case of a less massive binary that produces a remnant, which is likely to survive for substantially longer? Well, we expect that this merger process will strongly amplify the magnetic fields on small scales inside these neutron stars. It's possible that will translate into a large dipole scale if there's some kind of dynamo in these post-merger remnants. Highly uncertain. There are people on the line who know a lot more about this than me. But if this object is assuredly going to be rotating at near breakup, and it potentially could have a strong magnetic dipole. And so you could get a very rapid magnetic spin down of this object before it collapses into a black hole. And as I'll talk about, that could give rise to a brighter, faster, and bluer kilonova. And you may also see non-thermal emission from this millisecond magnetar that forms here. And the essential point is that when you have a prompt collapse or even a hypermassive neutron star, there's not that much energy liberated before you form the black hole. But if you require spinning down to form the black hole, then there's a sort of free energy that has to be released into your environment to make a black hole. So in other words, you can't just trap all of your angular momentum into the black hole's angular momentum. There's a sort of amount that you're going to have to emit. And if you form one of these rapidly rotating objects that doesn't collapse immediately, it could emit 10 to the 52, 10 to the 53 ergs into its environment. And this is substantially more than the kinetic energy of 170817. So this sort of spin down energy from the putative millisecond magnetar, its luminosity could actually substantially exceed that of radioactivity. So if this magnetar is able to power the event, it could end up producing a much brighter, faster evolving transient than we saw from 1707, because it's not powered by our process decay, it's powered by this pulsar in the center. So my final few slides are just to kind of give you, my kind of view on the future of this field. This was actually my student Ben Margolis's paper. The basic thing is that I think of this as kind of a Voigt-Russell theorem for binary mergers, that basically mass is destiny. The mass ratio does matter, but essentially the binary mass is, in my view, the dominant variable that will control the outcome. Because it probably controls when the black hole forms, which has some impact on the GRB jet. It controls how much mass is ejected, what is the composition of that mass. And we also expect theoretically that there could be abrupt qualitative changes in these properties as a function of the binary mass. And it turns out that LIGO is able to measure the binary mass well, because you can connect the binary mass to the chirp mass, and the chirp mass is what they really measure well. So essentially what we're saying is that if you start taking events and you start binning their outcomes, if somehow through the electromagnetic counterparts we can say, okay, this event was a hypermassive neutron star, this was a prompt collapse, this was a supermassive neutron star, this was a stable one, and start to bin them in this way, either empirically or based on some theory, then we can essentially hone in on some of the properties that are controlling the equation of state. We can hone in on the physics of these different defining these different boundaries. And this could be important for a number of reasons. It could help us prioritize follow-up if we're like, okay, this is another hypermassive neutron star in the era where maybe we have tens or hundreds of these, to decide which to follow up in a given period of time. Maybe we want to prioritize the ones that are in some ways different or are likely to give us brighter or dimmer counterparts. If it's far away, maybe we don't want to go after it if it's expected to be very dim. And also, any deviations from this would spell that our numerical relativity simulations are missing something. So if there's like a phase transition in the neutron star, it's not, may not conform to this nice ordering. And I think this is, and also I think this is a motivation. LIGO currently doesn't kind of keeps for good reasons, but they keep astronomers in the dark about exactly what are the parameters of their binaries. In the future, I think that may have to change if we're really going to use these outcomes to make informed decisions about what to do. And so this can be sort of also framed in terms of a multi-messenger matrix, where you're essentially trying to connect gravitational wave signature on one axis to the electromagnetic signature. And so this is essentially what I already said, that hopefully if we can create this matrix, not only can we confirm the expectations of numerical relativity, we can potentially constrain the equation of state. So in summary, this first neutron star merger by LIGO was really more than we could have asked for. It was really surprisingly well behaved compared to what expectations were ahead of time. This is showing you the time leading up to the merger and the time after the merger in sort of a logarithmic sense. And this is the event, the signal it produces, and phase. So initially you have the in spiral of the binary. I didn't talk about it, but there could be interaction between the magnetic fields of the two stars as they coalesce that could produce a radio or X-ray precursor. Then the two stars coalesce. You get the ejection of mass dynamically. You get the formation of a compact remnant, either a neutron star or a neutron star that collapses into a black hole. We think that this is the phase where it's accreting this disk that powers the gamma ray burst. If you have a long-lived neutron star, it could also possibly power, I didn't talk about this, but extended X-ray emission that is seen after some short gamma ray bursts for timescales of minutes or longer after the gamma ray burst. The expanding material from this is in most cases neutron-rich, and it will undergo an R process within seconds, but then will decay back to stable elements over timescales from seconds out to months. And this can power a variety of different thermal counterparts, which I refer to as the Kilonova, and they come in different flavors depending on the composition of the ejecta and what R process elements are actually created. There's some interesting stuff that can happen in the first hours, which relate to the fact that the very outermost layers of the ejecta may expand so rapidly that the neutrons can't get into the nuclei, they freeze out. And so you may get a decay of free neutrons on the very outermost layers in the first 15 minutes. And that could produce a fairly bright UV counterpart. This is of interest since the Israelis are now flying this ultrasat mission to follow up gravitational wave sources. This neutron precursor emission may be important. And then ultimately, whatever ejecta is there is running into the interstellar medium and producing the afterglow, which I also didn't talk about. But what did we see from 17817? Well, we definitely saw gravitational waves. We didn't see a precursor, but I don't think we have good constraints on that. We did see a GRB. We did not see any extended emission. We didn't get onto the Kilonova for 11 hours after the event, so we didn't see the neutron precursor if it was there, but we did see the rest of these things. So this was a very exciting event. And it's really remarkable the number of firsts that came from this discovery. It was the first gravitational waves from a binary neutron star merger, the first counterpart to a gravitational wave event, and really it was really a multi-wavelength. The first, sort of definitive connection to short gamma ray bursts. I didn't say this, but the jet we inferred from the off-axis afterglow, as far as we can tell, is fully consistent with those that we know power short gamma ray bursts at cosmological distances. The first time we've attempted, at least, to put gravitational wave and multi-messenger constraints on the neutron star equation of state. The first direct evidence for the creation of our process elements in the universe. And I also didn't talk about it, but it was the first redshift of a gravitational wave event that non-statistical redshift that allowed us to place a constraint on the H0. So this, of course, all my work was done in collaboration with a wonderful group I've had over the last few years at Columbia. And I want to thank you for your attention. Thanks.
Thank you for a very nice presentation. Now we'll have some time for questions. And I see the first raised hand by Paul Davis, so please.
Yes, hello. Thank you. Very nice talk, Brian. A related question. Do you have an opinion about the transuranic elements in Przynski's star, if I'm pronouncing that correctly?
I don't know. I'm sorry. Can you remind me that I've heard of this star, but I don't remember the phenomenon.
Right.
Yeah.
So this unpronounceable Polish gentleman was some decades ago an astronomer in Australia, and he discovered a star that has very peculiar spectral properties in relation particularly to heavy elements, including some transuranic elements.
Okay.
This hasn't gone away, and comes up from time to time in discussions in the SETI community. Is this some sort of weird alien structure or something? Let's set that on one side. The question is, would there be a natural explanation? It's not a neutron star. I mean, it's just a star, but it's got these really peculiar spectral lines.
Yeah.
But if you don't know about it, well, let me not.
I've heard of it, and I think I've heard of it, but I haven't given it recent thought. Yeah, I mean, I don't want to say something dumb here, but no. I would say, I mean, in principle, if it, these neutron star mergers could, in principle, we could imagine somehow happening nearby some star, but I feel like that would be a bit contrived. But
if anybody can come up with a decent explanation, it seems to be it. All right, so maybe you should check it.
I'll take a look at it. I think I'll definitely.
You can figure out how to spell it. It starts with a P again.
That's the first challenge. Thank you. I'll take a look.
Okay. Next question, Nathaniel Butler.
Brian, how you doing? Nice talk.
Hi, Nat.
Hey, quick question. I'm curious about, you touched on this at the end, the connection to short duration gamma ray bursts. I'm curious about your current view about sort of, how many of the short bursts we expect are, compact object mergers now, and how many are likely to have direct mappings to these LIGO events, and particularly the issues of jetting, I guess. If we think of cosmological short bursts as being on axis primarily, and this GW event was off axis, perhaps. What's your current view on how likely do we expect all short bursts to produce these kind of LIGO events, or is it some fraction you can estimate now?
Yeah. So LIGO's measured rate, as I mentioned, is uncertain, but it's between about 10 and a couple thousand. So there's this huge error bar in their rates. It's totally consistent if you take the beaming corrected short GRB rate. I think the unbeaming corrected rate is like locally 5 per gigaparsec cube per year, and there's probably a beaming factor of 100 or something. So I think we can't, it's consistent with all neutron stars making short GRBs and all short GRBs making gravitational waves. Of course, most of the short GRBs that we observe are happening at redshift 0.1 or above, between 0.1 and 1, and currently LIGO's reach is only extending to a few hundred megaparsecs. So I don't think there's, the fact that you probably know this, but the fact that we haven't seen gravitational waves from other on-axis short GRBs that we've localized at high redshift is not surprising. Of course, there is this question of, could a fraction of short GRBs where we haven't identified the redshift, could they actually be in the nearby universe and be off-axis jets, basically the analog of 170817. And I know there's been some work on this, and I remember Neil Tanvir a few years ago also had some work showing that there was and maybe there's more recent work, but showing that there's a correlation if you correlate the positions of short GRBs with local structure. You see something, that there's some hints that there may be a population of short GRBs that are at much lower redshift and could be sort of 170817 analogs. We have not seen, but we're now constraining that because with LIGO's, LIGO detected, would have seen, we would have been able to make that association. We've seen a few there are a few more neutron star mergers in 02 and 03. And we haven't yet seen any such association. So I think probably there's probably most GRBs are just currently at too high a redshift now. Now, of course, once they create these 3G detectors they're talking about, like Einstein Telescope or Cosmic Explorer, then they hope to be able to detect neutron star mergers out to redshift 1, and then essentially almost all of the ones we're currently detecting should have gravitational wave signals. So that's kind of exciting. But yeah, I think right now it's really hard to. I think the rates are consistent, but I don't think we can say for sure that there couldn't be multiple types of events contributing to short GRBs other than mergers. And of course, there's always the question of like giant magnetar flares in other galaxies that may look like short GRBs as well. So I'm sorry I didn't really answer your question, but.
No, that's good. Thanks.
Yeah.
Okay, next question is David Alvarez Castillo.
Yeah, hello. Thank you very much for this very nice lecture. I just have a question. Could you say something about the expected neutrino, the properties of the neutrino spectrum that's expected, as well as the maximum energies that you could sort of estimate for cosmic rays from this event?
That's a good question. I'm not the best to comment on that. The GRB, well, okay, so yeah, there's two types of neutrinos to be clear. So I talked in my talk a lot about neutrinos, and I was talking about kind of tens of MeV thermal neutrinos that are coming from the remnant or the disk, which have an extraordinarily high luminosity, like 10 to the 52 or 53 ergs per second, but probably will be very hard to detect because we don't have as sensitive of neutrino, neutrino cross section is increasing with energy. And so we don't have great sensitivity to MeV neutrinos. Stated another way, there's many more core collapse supernova in the universe than neutron star mergers. And, we still have only detected essentially one core collapse supernova neutrino is the one that happened in our own galaxy. But yeah, so I think you're more interested in the high energy neutrinos that may be produced by cosmic rays accelerated at the GRB jet. And I could refer to you to a paper. Kota Marase has written some papers on this, and Kai Fong, and recently there was I'm blanking on who else wrote a recent paper on this. I'm sorry, but I could if you email me, I'll send you some references. I think it's very uncertain because it depends on exactly what is the internal dissipation process that is powering the GRB. If it's internal shocks or whether it's something else, you're going to get different predictions for that. But I do believe that the expectation were that that at our viewing angle, it's not surprising that IceCube didn't see any neutrinos from this event, given the jet power and beaming and things. But if we had viewed 17017 on axis, some of the models would have predicted some IceCube neutrinos, I believe, like realistic models. So that would be implying particle acceleration up to 10 to the 15 or so. But I have to give you the so if you send me an email, I'll send you the appropriate references, but I don't have them right here.
Thank you very much. I'll email you.
Thank you.
Well, next question is from Axel Brandenburg.
A very nice lecture, very inspiring. You said in the beginning that there could be multiple outcomes from the collapse. And then towards the end, you flashed something about the Vogt-Russell theorem. So could you please explain that? Would, of course,
sorry, this is my
this was my
inelegant. This is my inelegant. Maybe I'm misattributing the Vogt-Russell theorem, but I'm thinking of it as basically like the idea that yeah. So that has to do with sort of uniqueness of Vogt-Russell theorem, but I'm thinking of it as more along the lines of mass is destiny, meaning just that once you've defined the mass of the ingoing binary, it's basically the dominant variable that controls things. So that may be different than the Vogt-Russell theorem. But that was what I meant was essentially that of all the things we could vary, basically the mass ratio of the binary or the total mass is essentially the thing that will determine these outcomes. That's all I meant.
Yeah, right. Yeah, I guess that. Thanks very much indeed.
Yeah.
Okay, thank you. Let's see if there are some more questions. I had some sort of very simple question. At some point, you mentioned that when you have relatively low total mass of the merger, then you could have the supermassive star, and it potentially could be Magnetar. So what exactly are the conditions that you actually form a Magnetar from such kind of merger?
Well, I think it's very likely. I think all the simulations agree that unless the object promptly collapses into a black hole, which we think is not the case, you're dissipating so much shear energy in this event. MHD simulations have shown this, that it's unquestionable that you amplify the magnetic field in this differentially rotating, near breakup rotating neutron star to 10 to the 16 Gauss, if not higher, and through Kelvin-Helmholtz instabilities, the MRI, various things. So and just linear winding will get you there too. So I think it's very likely that if you define a magnetar as just some object that has an interior field somewhere of 10 to the 16 or 15 Gauss, then it's unquestionable that these remnants are magnetars. it's more highly uncertain whether they will have an ordered dipole component ultimately that is even a fraction of that. But the question then is, how long does that magnetar really live? Because as I mentioned, if it's one of these hypermassive stars, it's bordering on instability, and as soon as it redistributes its angular momentum just a little bit, it destabilizes and collapses. So it's very likely a magnetar. It's just maybe a magnetar that lives for 10 milliseconds or 100 milliseconds. What would be exciting would be these magnetars, which if the equation of state is pretty stiff and the maximum mass is pretty high, and we get a very low mass binary, then the current indications are that it could survive a lot longer, because even when it's even given its total angular momentum of the merged system, if it were in a solid body state, it would still be stable for sufficiently low ingoing mass. So those objects could be fascinating because they they have an enormous rotational energy, and if they do have this dipole component, then there's a way to tap into that. But it's an important question whether they will acquire this dipole. There's been some recent work on alpha omega dynamos and protoneutron stars, which suggests that if they're rotating this fast, this goes back to Thomson and Duncan and more recent work, that they should acquire ordered magnetic fields that can be of this strength. So yeah, that would be very interesting. I should also say that even if it's a magnetar that only survives for 10 or 100 milliseconds, it may still have a really important effect on the environment and ejecta of these events, because the object is hot, so it's radiating neutrinos, and neutrinos are ablating mass from the surface of the magnetar. This is very well known from protoneutron star literature. But if you add an ordered magnetic field to the mix, then you've essentially created a magnetized star where the magnetic fields are causing the fluid above the star to co-rotate with it, and you substantially enhance the mass loss rate from this magnetar before it collapses. So my view is actually that the blue I didn't talk about it, but my view is that the blue component of the kilonova in this event could well have been wind from the magnetar that only lived for 100 milliseconds. Rather than coming from any form of dynamical or disk wind outflow, I actually think it could be a magnetocentrifugal wind from the remnant. So anyways, there's a lot of magnetar can do, whether it survived for 100 milliseconds or days, potentially.
That's kind of impressive. Thanks. Any other questions before we wrap this up? I don't. Okay. Go ahead.
Okay. First, I'm old here. My glass got yesterday. I can't follow it, but all the time here. Can you see the slides again? Is a record for look on the slide again, weekend?
Yeah. Yes.
I will post the slides. You will find the links on Inspire.
Okay. Thank you.
Okay, I don't see any raised hands, so I would like to use this opportunity once again to thank Brian for a very nice presentation. And with that, we will wrap up the official part.
Okay, thank you.